Okay, next speaker is invited speaker Kunihito Ioka, talk on fireball in fast radio burst.
Okay, thank you very much for giving me a chance to talk about fireball in fast radio burst. My name is Kunihito Ioka from Yuka Institute, Kyoto University. And this is a collaboration with Tomoki Wada and Wataru Ishizaki, so previous speaker. And as you already know, the galactic FRB has a smoking gun that magnetizes one of the origins of FRBs. And this event is also very important, that the energy of the magnetar burst is much larger than the FRB energy. As you see, so luminosity of the X-ray is 3 orders of magnitude greater than the FRB. So this means that the X-ray magnetar X-ray flare burst is the main event, and FRBs are just a sub-event. So we have to first understand the X-ray magnetar burst rather than the FRB. So in order to understand the FRB, we have to understand the X-ray burst first, and in that context, we study the FRB. We should study the FRBs. There are many discussions about the emission site. One is the magnetar sphere model, and the radius is much smaller than 10 centimeter. And the other is the outflow or faraway model, and this is the radius is around 10 to 13 centimeters. So the difference is more than three orders of magnitude, and this is a kind of the most unknown phenomena in the universe. So today I would like to ask a question in a different way. How to transfer the energy from the surface of the magnetar to the emission zone. So I'm very sure that the energy is generated near the surface of a neutron star. This is one reason is the energetic reason. The energy of the magnetic field is dominated by near the surface. So in order to provide a lot of energy, the emission site should be near the surface. Also, there are recently observations that there is a glitches associated with FRBs that also strongly suggest that the emission site is near the neutron star surface. So then how to transfer the energy from the surface to the emission site? So I forgot to mention that the FRB should be produced not near the surface, because if the FRBs are produced near the surface, their energy, FRB energy, is attenuated by various processes. So FRB is not near the surface, but the energy is generated near the surface. So one of the mechanism is the pointing flux. This is frequently discussed, and I will mention about it at the later of my talk. And the other way to transfer the energy is kinetic energy. And this is a kind of fireball model. And the fireball is, so if the thermal energy is generated near the surface of the neutron star, it creates a fireball. So thermal energy creates E plus electron and positron. and electron-positron can expand by its own pressure and converting the thermal energy into the kinetic energy. And the kinetic energy can transfer the energy from the surface of the neutron star to the outward. And actually, traditionally, so in order to explain the magnetar burst, a trapped fireball model is discussed. And in this model, thermal energy creates E plus minus surrounding the neutron star, and this trapped surface emits X-rays. Actually, given the luminosity of the X-ray and the temperature, we can calculate we can estimate the size of the fireball. It's around 10 to 4 centimeter for the case of the galactic FRB, and this is much smaller than the size of the neutron star. And this estimate is just the assumption of the black body. And in the galactic FRB, the temperature was very high compared to the previous magnetar burst. This is so this cutoff energy for the galactic FRB, and these are the cutoff energy for the other magnetar burst. So this is around 10 kilo electron volt. This is near the 100 kilo electron volt. So because of this high temperature, the fireball is completely optically thick at the surface of the fireball. This is the optical depth at the trapped fireball surface as a function of the temperature cutoff energy of the fireball. And for typical so magnetar burst, so optical depth can be smaller than unity, but for the galactic FRB, temperature is high, then the optical depth can be much larger than unity. This means that the X-ray from the trapped surface create E plus minus outside the fireball. So this means that and E plus minus is created by X-ray tail. So usually spectrum has a tail, and some photons are very high energy, and high energy photons can create E plus minus. And so then we can conclude that the magnetic field surrounding the trapped fireball should be open field. Otherwise, so the following things happen. If magnetic field were closed, something like that, then so because the fireball is optically thick, X-ray from this fireball create E plus minus outside this fireball. And if the magnetic field were closed, then the trapped fireball become bigger. And as you remember that if the size becomes bigger, this observation cannot be explained. So in order to explain this observation in the context of the fireball, trapped fireball, then we should consider some expanding fireball also. And if the fireball expands, density decrease, and optical depth decrease, then finally X-rays can escape from the fireball. This is so escape this problem. And so in this event, in order to explain the X-rays, so we should consider some expanding fireball that transfers the energy from the surface to the up to the photosphere, up to the photosphere. where the optical depth is unity. In this scenario, the fireball can release the photons with energy of the initial temperature of the fireball. So observed temperature of the fireball can be equal to the temperature of the initial fireball. Initial fireball means that the temperature here. Even if the fireball expands, and due to the expansion, temperature usually decrease, but at the same time, Lorentz factor of the fireball increase, then blue shifted temperature it becomes constant, cancel with each other, and initial temperature is observed. So this is the case of the spherical case, and this is the case of the dipole flux case, and in both cases, initial temperature is conserved. And we can also consider more details to consider the fireball evolution. For example, baryon contamination at the near the surface, and also the photon escape from the photosphere, and photon escape from the diffusion in the lateral direction, and so on. And but I don't have time to explain the details, and combining these effects, and this is a summary of the results, and this is a radius, and at the same time this is the Lorentz factor, and as a function of the dimensionless entropy. And this means that if this parameter becomes large, the baryon is poor, and if parameter is small, baryon is rich. And for a given initial condition, fireball expand, and so evolution follow in this direction for a fixed eta value. And then, as the expansion, as the fireball expand, and so fireball is accelerated due to its own thermal pressure, and the density decrease, so the optical depth decrease, and finally, optical depth becomes unity, and the photon can escape from the fireball. So this is the radius of the photosphere, and at that time, Lorentz factor can be about 10, and this Lorentz factor can be changed if you change the baryon contamination, and in this case, it's up to 100. And more than that, so radiative acceleration is also very important for this system, and so electron and positron and even proton and are accelerated even above the photosphere. So, and this is done by the, for example, Thomson scattering, and if the work done by the photon becomes larger than the rest mass of the particle, the acceleration continues, and so the effect of the radiative acceleration is more important by the resonant cyclotron scattering. This is a Thomson scattering, and this is a resonant cyclotron scattering. So, and because there is a magnetic field, so there is a resonant cyclotron scattering, this effect is more important than the Thomson scattering. And then by considering that, so fireball can be accelerated further up to here, so Lorentz factor can be up to 100. And then, so final luminosity is something like that. And this is the luminosity of the fireball for given thermal energy. So this means that if for the electron and positron fireball, the conversion rate is just -6 to -4 or something like that. And if you consider the baryon, and then conversion rate becomes larger and larger at if the baryon contamination becomes large. And this is the luminosity of the true luminosity, and so isotropic luminosity is the observed luminosity, and this should be corrected by the opening angle of the fireball and the Lorentz factor of the beaming, relativistic beaming of the fireball. And by considering that, behavior is a bit complicated depending on the emission radius, and gamma effect relativistic beaming can increase the isotropic luminosity, and if the theta becomes large at large radius, then the isotropic luminosity becomes smaller. In any case, so observed ratio between the X-ray and the FRB is about -10 to -3, and this line can be achieved for the baryonic fireball, and in some cases, even for the electron and positron fireball, it is also marginally possible if the emission site is close to 10 to 8 centimeter or something like that. So the conclusion in the first half of my talk is that kinetic energy can be provided by the fireball, and we can consider a situation that the fireball radiation is comparable to the X-ray luminosity of the magnetar burst, and the fireball kinetic energy can be larger than the FRB luminosity. And in this case, in this acceleration, baryon or resonant scatterings are very important. Okay, let's go to the second half of my talk, and this is due for the alpha-band waves. In order to understand the alpha-band wave contribution, the evolution of the wave amplitude is very important. And wave amplitude is like this, so perturbation of the alpha wave and background magnetic field. And this ratio becomes grow as a function of the radius. This is derived from the luminosity of the alpha wave. This is about constant. And this means that delta B is proportional to R2 minus 3/2. On the other hand, the magnetic field of the dipole configuration decays as R2 minus 3. So this ratio becomes R2 3/2. And this means that this ratio becomes about unity, so becomes nonlinear at the radius of about 10 to 9 centimeter below the magnetosphere. So, and in the previous talk, Ishizaki-kun talked about the nonlinear interaction or nonlinear decay of the alpha waves, parametric decay of the alpha waves. So, in this decay mode, so this is frequently discussed in the solar physics, and the alpha wave decay into the alpha wave and the acoustic wave. This is three-wave interaction, and the acoustic wave, so, and this is slow wave, makes shocks and dissipate. This means that effectively alpha wave decays into the thermal energy. And the growth rate is obtained in the solar physics, but this is for the non-relativistic case. So we extend this formula to the non-relativistic case. And so sound wave becomes dissipated in the thermal energy like this. So usually sound wave becomes non-linear in a very short time scale, and this means that effectively alpha wave energy goes into the thermal energy of the fireball. And this is a summary of the decay rate of the alpha wave. And the alpha wave decay rate is determined by the amplitude of the alpha wave, and also the sound wave of the matter, and also sigma parameter. The sigma parameter is the energy density ratio between the magnetic field and matter. So, and so something could happen in this expanding fireball due to the alpha wave decay. And alpha wave energy can be converted into the fireball energy, and it may produce FRB. And but today I don't have any conclusion. And today I just calculate the decay time divided by the dynamical time of the fireball, and as a function of the radius. This is 10 to 6 centimeter, this is 10 to 7 centimeter, this is 10 to 8 centimeter, this is 10 to 9 centimeter, and the ratio alpha wave decay time decrease like this and touch to the unity within the light cylinder, magnetosphere, and also within the linear stage of the alpha wave. So linear alpha wave can decay into the thermal energy of the fireball in the before becoming the non-linear stage, and then maybe alpha waves can heat the fireball matter, and then because of the decay rate is proportional to like this, if the matter is heated, sound wave becomes large, then the decay rate becomes slow. Then this follows the unity as the temperature of the fireball becomes larger and larger, and finally reaches the relativistic temperature. I don't know what happens after that. And also, we should also consider the X-ray background. X-ray can inverse Compton of the heated fireball. It can decrease, keep the temperature very low. Then this instability can continue. So it may explain the non-thermal X-ray photons of the X-ray burst. And maybe I don't have time, so let me summarize my talk. So expanding fireball could explain the X-ray of the magnetic burst, and also the kinetic energy may explain the FRB energy. And fireball model in general provide a lot of matter to the surrounding, so it may explain the dispersion measure variability. And also in this scenario, alpha waves can decay in the fireball, and that may explain the non-thermal X-ray of the magnetic burst. Okay, that's all. Thank you very much.
Thank you, Kunihito, for very nice summary of your research. Okay, we can have maybe a couple of questions. Kazumi first. Please go ahead.
Thank you. If I understand correctly, you treat the expansion of the fireball and the propagation of alpha wave independently so far. I mean,
so we consider every physics in the co-moving frame of the fireball.
I mean, when you, for example, discuss about the propagation of alpha wave, the wave is propagating not through the fireball but through the I mean,
Alpha wave can propagate through the fire.
so that kind of effect is have been already taken into account. I mean,
What do you mean?
when you solve propagation, perturbation equation for the alpha wave, so the background plasma density and so temperature and so on is determined from the, well, is consistent with expanding fireball or?
So we consider it's a perturbation. So there is a homogeneous fireball and consider the perturbation.
Okay, yes, yes. So background is already fireball.
Yes.
Yes, thank you.
So just a plasma. So constant plasma. Low temperature, constant plasma.
Then is it okay? Fireball can be heated up. I mean, you assume the cold ionized plasma.
Yes.
That is consistent with the fireball, which might coexisting with the alpha wave.
Yes, yes.
Yes.
And so expansion time scale is much longer than the frequency of the alpha wave. So period of the alpha waves.
Okay. Any more question? Okay. Maybe there are also online questions. So maybe.
Yes, one online question by Zhao Zhang.
Okay, can you hear me? Sorry.
Yes.
Okay. Oh, thanks for your wonderful talk. So I have maybe a naive question about the energy generation and the efficiency of your model. So we know the magnetar can produce energy by magnetic radiation or some crust crack. So in your fireball model, what kind of energy generation process it is?
Yes. So in my talk, I don't specify any specific model for the energy generation. And my standpoint is that the energy generation mechanism is not known. So we cannot specify what fraction of the energy goes into the kinetic energy, what fraction of the magnetic energy, we don't know. So something should happen near the surface. It may be reconnection or some starquake or something like that. And I'm very sure that something should happen near the surface. But I don't know what is happening. And so my standpoint is that we should be open-minded the fraction of the kinetic energy and magnetic energy.
Okay, thank you. So the second question is, we know the energy can be dissipated by the radiation, like the X-ray burst or the faster radio burst. So did you ever estimate the energy efficiency of this process? Or what percentage can it reach?
Energy dissipation? What do you mean?
Yes, yes. Energy efficiency of the fireball, of the energy.
Oh, so most parameter efficiency of the X-ray photon, most photon thermal energy X-ray photons efficiency is almost 100%. And if the baryon is too much, then photon, so efficiency becomes low. But the almost all cases, most energy escape as the X-ray photons. And only a small fraction of energy goes into the matter.
Okay, thank you. Thank you very much.
Thank you very much.
Okay, we can have a last quick question from Ellis.
Sure. So with this,
Just a moment.
Sorry. Thank you. So with this alpha heated fireball, I'm curious, what would the impact of baryon contamination be here?
Yes, that is very important question, and I don't have an answer.
Oh.
And actually, so if the baryon is dominated, this inverse compton is not effective because the cross section is very low. And then the temperature does not decrease, so temperature like so increase up to this energy, but above this temperature, thermal, so energy density of the matter increase further. This means that sigma increase. Sigma increase means that the rate becomes slow. Increase. So then this becomes something like this. So then in any case, so heating continues. So in my current understanding, but still under investigation. So
Thank you very much. Very interesting.
very interesting.
Okay, it's right time to stop. So let's thank again for Kunihito for nice talk.